So we are starting. So very good morning, respected resource person, coordinators, and participant. We welcome you all for the day 10th session. So today is the last day. So on behalf of E&ICT Academy, IIT Guwahati, and MNIT Jaipur, we would like to invite Shri Bijit Vishwas Sir, Samir, Kolkata. Bijit sir has received the BTech and the MTech degree in Electronics and Telecommunication Engineering from Jadavpur University, Kolkata in the year 2002 and 2007 respectively. Presently, he is working as a scientist C in Society of Applied Microwave Electronic Engineering and Research, Samir, Kolkata, which is running under the Ministry of Electronics and Information Technology, Government of India. He is also involved in the field of design and development of microwave, millimeter wave circuit, subsystems, and systems for more than 13 years. He has published more than 20 research articles in various international journals and conferences on millimeter wave circuit. He has also successfully completed more than 12 R&D projects at different frequencies, ranging from S-band to W-band, sponsored by Government of India Agency, DRDO, MIT, or Ministry of Electronics and Science. His research interests include simulation, modeling, and design of millimeter waves, active as well as passive circuit, MMIC design and packaging, and substrate integrated guided circuit. He is also a senior member of IEEE journal. So with this, we would like to invite Bijit sir to this platform to please start the session, sir. Sir, over to you, sir.
Yeah, a very good morning to all the organizers and the attendees. Thank you very much for your kind introduction. So I am going to start my presentation today. Again, very good morning to everyone. Myself, Bijit Biswas. I am working in the Circuits and Division of Samir Kolkata Center. So my today's talk is on design of millimeter wave MMIC based frequency multipliers. These are the topics I shall be discussing today. We will start from the basics of millimeter wave technology, then we will see what are frequency multipliers, then we will see what is monolithic microwave integrated circuits, in short MMIC. Then we will show some of the MMIC circuits that we have fabricated and tested at Samir Kolkata Center. We have designed the same. There, I shall be covering 4 MMIC based frequency multipliers. You can see here one frequency tripler, one quadrupler, one frequency doubler with integrated output amplifier, and another frequency tripler with integrated integrated output amplifier. All are in millimeter wave frequency band. And finally, I shall talk about the MMI building and how to package. So the first topic is millimeter technology. Most of you are already familiar about the technology. We can see here there is an exponential increase in demand of transfer rate in wireless communication from first generation of 1980 to the present generation of fifth generation communication. And we can see here the data rate is increasing from 2.4 kbps to 10 gbps at present. Now we see that to achieve high data rate, bandwidth, and as per Shannon's theorem, the upper bound of the capacity of a link is given by this formula, where the channel capacity is related to bandwidth and signal to noise ratio. Here we see the millimeter wave frequency absorption characteristics of the atmosphere. We see that the microwave frequency ranges from 3 to 30 gigahertz and millimeter wave frequency ranges from 30 to 300 gigahertz with the corresponding wavelength of 10 millimeter to 1 millimeter. Similarly, the microwave frequency range corresponds to wavelength of 10 centimeter to 1 centimeter. So we can very well say that microwave are centimeter waves. From these absorption characteristics, we can see that there are principal windows. That means there are some frequencies at which the millimeter wave absorption is low in the whole frequency spectrum, that is at 35 gigahertz, 94 gigahertz, 140 and 220 gigahertz. So we can use these frequency bands for millimeter wave communication. And there are corresponding high large bandwidth, that is 6 gigahertz, 23 gigahertz, 26 gigahertz, and 70 gigahertz, corresponding to each of these millimeter wave windows. So we see that as we go higher and higher in the frequency band, we have more and more bandwidths available. We can also see from this absorption bands at 60 gigahertz, 119 and 183 gigahertz. That means at these particular frequencies, there are atmospheric attenuation or absorption corresponding to some particular gas like oxygen or humidity. So absorption is high at those particular frequencies, but these absorption bands are also associated with large bandwidth of more than 10 gigahertz. So we can use these absorption bands for short-range, highly secure communication. Since attenuation is high, we can be assured that the signal won't reach beyond a certain range, so the secured. There are certain features of millimeter wave technology. It has potential to meet requirement of future wireless communication with data rate support up to 10 Gbps. Some of the applications includes high-speed point-to-point wireless LANs and broadband access, mobile and wireless networks, streaming high-resolution video, automotive radar, and there are also some disadvantages as well. Like there are other advantages of millimeter wave that includes large bandwidth that supports 10 Gbps or more to 1 Gbps using microwave links, and there are small components available, and the transceiver and antenna fabricated on a single chip. There are other advantages like greater resolution, this higher bandwidth and lower wavelength help in achieving higher range and cross-range resolution, and low interference and increased security, an added advantage due to the narrow beam and short range. There is less chance of interference from nearby radios. It is much harder to intercept the signals, and there is increased security. The signal only restricted to a small area. There are challenges
Excuse me, sir.
Yeah.
Yes, sir. Sorry for interrupting in between. Actually, sir, the volume is little bit low. If you can just higher little bit the volume.
Okay.
Yeah.
So, okay now?
Yes, sir. Now it is perfect, sir.
Thank you.
Yeah. Thank you, sir.
So,
Thank you, sir.
there are challenges associated in using millimeter waves. It has limited range, as we were discussing, and the attenuation is higher during fog, rain, and moisture. And the range can be extended by using high transmitting power, antenna gain, and transceiver with high sensitivity and low noise figure. But these are all costly, and it requires costly infrastructure, and line of sight is required, otherwise trees, buildings that may block the waves, so the signal strength is reduced. Now here we see the 5G communication bandwidth. The most of the 5G communication in a subscriber driven market will be in sub 6G bands for mobile communication. But for high-end 5G applications, it will be implemented in higher frequencies from 24 to 100 gigahertz band. There are several bands for a higher frequency 5G communication. You can see from here. You can also see that the 60 gigahertz band is unlicensed. So there are many research work going on worldwide for 5G millimeter wave communication at 60 gigahertz and above 100 gigahertz. From 100 to 300 gigahertz band, this frequency band will be utilized for next generation 6G communication. So we can see the contribution of millimeter wave technology in 5G communication, and mostly there will be a cognitive radio concept in for better utilization of spectrum at 5G millimeter wave. There are the feature of cognitive radio network. It is in that concept, unlicensed system can utilize the same spectrum resolution with the licensed primary system, either based on an interference-free mode or interference-tolerant mode. So with that, I am coming to the frequency multiplier basics. So the very basic thing is that as we have seen, there is rapid increase in demand for higher data rate. The wireless transmission with high data rate requires higher RF bandwidth. We have already seen the unused spectrum resources at the higher frequency bands can be utilized. We have seen from the atmospheric absorption characteristics of millimeter waves. The millimeter wave wireless transceiver systems requires stable local oscillator reference at millimeter frequency bands. But local oscillator in wireless transceiver system and produce phase modulated noise components. Here from this figure, we can see the spectrum is very clean. When we are seeing it at 5 gigahertz band, it is a W band signal. So when we see it at 5 gigahertz band, we can see only a spike. But when we just zoom into the signal and see it with a very close span of 5 megahertz, the actual signal is like this. So that means there is no pure spike available in reality. So all the power that we see, that is spread over its adjacent frequency bands. So the power associated with the adjacent frequencies, that gives the estimation of phase noise. The more pure is the signal, the narrower is the spike. So, and the wider is the signal, the phase noise is more. So for communication, we require a signal reference which will give us a very low phase noise. Now, how to achieve a signal reference at millimeter wave frequency with very low phase noise? Here we see the frequency multipliers, a symbol of that. We give input frequency at F in and the output frequency we get at nth harmonic of the fundamental frequency. The frequency multipliers are frequency translating components producing the nth order harmonic of the input fundamental frequency. Now the frequency multipliers require some nonlinear semiconductor device to produce the frequency multiplication. For example, we require varactor or varistor diodes, which are passive components, and FET or PHET to realize active frequency multipliers. Now, this LO reference at millimeter wave frequency can be generated in two ways. We can have a single oscillator at millimeter wave frequency, like a VC. We can have a low frequency oscillator, maybe one lower frequency VC or a PLL, and then the frequency is multiplied using a millimeter wave frequency multiplier. Now, what is the advantage of using frequency multipliers? The phase noise density to output power ratio of an oscillator is proportional to output frequency square upon square of the quality factor. So we see that high frequency oscillator suffers higher phase noise. Phase noise degradation used by a is proportional to n square, where n is the frequency multiplication order. Now this oscillator multiplier combination, it exhibits lower phase noise characteristics. So with phase noise reference, we can have better quality of communication. So for millimeter wave communication, we require frequency multipliers. Now, these millimeter wave frequency multipliers can be utilized broadly in three ways. The first one is based passive multipliers, where the conversion efficiency can vary. For varactor-based multipliers, it is high. For varistor-based multipliers, it is low. It can show broadband performance. It has sometimes some reliability issue, that for waveguide-based configuration, for waveguide-based configuration, the reliability is not that good. For discrete FET-based multipliers, we can have low conversion loss, that we can have advantage of inherent input-output isolation. The PHEMT-based frequency multipliers in MMIC form is another type of frequency multipliers, where we have good conversion efficiency, we have repeatability and reliability, size and weight, and it do not suffer from package parasitics. Like in case of discrete devices, we need to package the device in order to integrate it in the circuit. But in case of MMIC, the passive circuit and the active circuit is grown on a single substrate, so requirement for packaging of the device separately is not there. So package parasitic related issues is not there. This parasitic effect actually limit the frequency of operation of the device, and it is also cost effective for volume production. If we go for very low volume production, in that case MMIC is costly, but if we can produce in numbers, in that case the effectively cost will come down. Now we will see what is monolithic microwave. So in short, it is called MMIC. Monolithic means carved out of a single stone, and MMICs are fabricated using a single mold of semiconductor material, and all passive and active circuit elements are grown over it using various lithographic processes. MMICs use an insulating crystalline material as both the dielectric and the active layer material. This permits the integration of active devices, control devices, transmission lines, and passive elements on a single substrate. So from this single substrate concept, the term monolithic comes. There are many MMIC foundry worldwide. So each foundry is having their own process. So there are different technologies like gallium arsenide based technology, gallium nitride based technology, silicon germanium based technology. So for gas foundry, we can name Tricoint Wind Semiconductor, OMIC UMS. For gallium nitride based foundry, we can name Tricoint, Raytheon, Neumann, Cree, and others. For silicon germanium foundry, we can have Freescale, IHP, IBM, etc. So there are some foundry. Sometimes we have access to them, sometimes we do not have access to them. So based on our selected technology, we can contact the foundry for fabrication of our designed MMIC. So here we see the MMIC design flow. It starts with the end user, who will specify the performance specification as per his requirement. Then based on the specification, we can have the design configuration. The design configuration is also based on the technology capabilities and process information, both coming from the foundry. And when we have finalized the design configuration, we can go to circuit design. The circuit design requires component models, which comes from the PDK of the foundry. PDK means process design kit. And also we require active device model, that is also coming from the PDK provided by the foundry. So after we get our circuit design, we need to simulate our circuit by using some CAD tool like ADS. So we need to do the circuit analysis. There are several analyses required for different kind of circuits. For example, for frequency multipliers, we require harmonic balance analysis and S parameter analysis. So when we have a circuit analysis, we do it in schematic layout. Then in the schematic simulation, we need to optimize it. When we optimize the schematic, then we will go to the layout generation. So when we go to the layout generation, then we can do the EM simulation. In the EM simulation, we can see the interaction between the passive circuits. We cannot do active circuit simulation in EM simulation or in layout. So in layout, we will model all the passive parts of the circuit and carry out the EM simulation. We will generate a S parameter file from the EM simulation, and then we will optimize the layout, and then we shall come back to circuit analysis again and do a co-simulation between the passive model of the EM simulation generated in the layout, and we will use the active device model in the schematic itself. So schematic will do a co-simulation using the active circuit model and the layout model generated in the EM simulation, and the final simulation will be in schematic itself. So we will get the co-simulation result. When we are satisfied with the co-simulation results, we shall go to design verification based on the design rule check, in short DRC, and fabrication rule check provided by the foundry. This design rule check is also provided by the foundry. So after the design verification, we shall generate the actual chip layout that will be provided to the foundry for fabrication. There we need to provide bond pads and some marking text and also some boundary lines as per the guideline of the foundry. So after this chip layout is generated, we need to share the chip layout in the specific format like PDS to the foundry. There the foundry will check the layout verification, and after the verification, they will go for fabrication. After fabrication, the foundry will inspect the fabricated chips optically, and sometimes they can provide the testing service also. So after the optical inspection, they will dice and deliver the chips. Dicing means they will cut out each chip from the whole wafer and provide the chips in a proper waffle pack or other. So here we see that MMICs, we have actually fabricated our different designs on UMS based on gallium arsenide based PHEM technology, PH15 from UMS, in a full 6-inch wafer run. So there we have put 21 different MMIC circuits, including 4 frequency multipliers that we are going to see in details today. So in along with other designs, we have put these 4 frequency multipliers, and we have fabricated the whole wafer in a 6-inch gallium arsenide based technology. So this PH15 is a gallium arsenide based PHEM technology with gate length of 0.15 micrometer, from which this PH15 comes, and the gate width and number of fingers can be chosen as per the circuit requirement. The FET models are available like small signal model, hot FET model. Hot FET models can be linear or non-linear, and cold FET model are non-linear models. The difference is that in hot FET model, it can draw ID or drain current, but the cold FET model cannot draw ID or drain current. So cold FET models, using cold FET models, we can design passive multipliers or passive mixers, but using hot FET model, we do active circuits. And while choosing the technology, we to see the maximum resonance frequency F max and current gain cutoff frequency FT and maximum frequency of model validation that we have to check. Sometimes the foundry provides the process design key, that PDK, and at that time this PDK will show result at high frequency also, but the model may not be that accurate. So we need to know from the foundry that up to which frequency the models are validated, so that we can comfortably do our design and we can have the confidence that this model will work. So this foundry will actually specify the power rating of the process in terms of watt per mm for that particular process. For example, for PH15, it is 250 milliwatt per mm. That means they specify the power in terms of length of the gate. So suppose we have a FET of 75 micrometer gate width and 4 gate fingers. That means we will have the total 4 into 75, that means 300 micrometer, and if we multiply 300 micrometer means 0.3 mm. If we multiply 0.3 mm with 250 milliwatt per mm, we will get 75 milliwatt. So that means FET with this technology of 4 gate fingers and 4 gate fingers, we will get maximum output power of 75 milliwatt. So we need to calculate what should be the maximum output power. So this is the fabricated wafer that we got from EMS France. We can see there are repetition of one tile. In one tile we have all 21 designs, maybe 1, 2 or multiple times. So this same tile is repeated throughout the wafer. So based on, we need to first design components, then we need to design the tile, then we can share the tile with the foundry. The foundry will put the tiles in the available space of the wafer and they will fabricate, and after fabrication they will dice each chips and send us back. So what are the design considerations for MMIC based designs? The device model, the selection are based on application and frequency of operation. As the gate width and number of fingers increases, gain decreases and power handling capability increases. As we have seen in our previous example, when we increase number of gate finger and gate width, we get more output power. But as the gate area is increasing, the gate to source capacitance is also increasing, which will limit the frequency of operation. So the gain will come down. The scalable linear models can be used for LNA design. Non-linear hot FET models can be used for non-linear components like power amplifier and frequency multiplier design. Non-linear cold FET models can be used for passive components like switch and passive mixer. Linear simulation, non-linear simulation, transient simulation, everything we need to check based on the application of our circuit. The EM analysis for high frequency operation is required, DC analysis for DC coupled active elements, tolerance analysis, stability analysis, all these things are required. Stability analysis is required from DC to at least twice the frequency of operation for to see whether the circuit is going to oscillate or not. And the design rule check is required to verify the compliance of the design with the foundry, as we have already seen. Now we are coming to the actual design of our circuit. The first one is a MMIC based frequency tripler from 15.67 to 47 gigahertz. So here is a very generic block diagram of a FET-based frequency tripler. The input is coming from 15.67 gigahertz. Then we have biasing network for gate bias. Then we have input matching. This is a common source FET-based design. And we have output matching network and output bias network for drain bias. And finally, we have the output frequency at 47 gigahertz. That is the 3 times of the input fundamental frequency. So here we see the preempt of gate length 0.15 micrometer and gate width of 120 micrometer. That is 4 gate fingers, each of 30 micrometer width, is used for this frequency multiplier design. For the required performance, the nonlinear hot FET model is used for simulation. Harmonic balance simulation is used in ADS schematic wizard. S parameter simulation is used to check the stability. Layout generation in momentum is following. But when we actually generate the layout, we need to check the layout rules that is provided by the foundry. And final optimization is done through co-simulation between schematic and layout. We need to check the yield analysis. That means every process has its own tolerance. So if this during fabrication, the tolerance will be there. Now if the tolerance is there, how much degradation is happening to our circuit, whether that is allowed or not, whether that is acceptable, that we have to check. If we see that there is too much of variation, then we need to change our design, and we need to have at least 85 yield for going to the fabrication, otherwise the fabricated circuit may not work. And finally, we have to check the design rules. So there is the frequency tripler simulation structure that is being simulated in ADS momentum. You can see we have 3 rectangles on the left and right. These are for connecting the device using this GSG ground signal ground pads. Coplanar probes can be probed on the circuit so that we can test the circuit. And we have the active device, and we have microstrip based stubs for matching, and also for the VG and VD biases. And when we fabricate it, that is exactly like whatever we have simulated in ADS. Chip size here is 1.5 mm cross 2 mm. So after we fabricate our chip, to test the chip. So for testing MMIC chip, we require probe stations. We have one cascade made probe station, Summit 12651B, and we also, that is for connecting the MMIC to the external test and measurement instruments. So in this monitor, you can see the image of the chip that is within the probe station on the left. So within this chamber, the chip is there. We are probing the chip using RF and DC probes, but it is so tiny we cannot see it through our eyes. So we can only see it in this microscope. The digital microscope captures the image and provides it in the monitor. So seeing the monitor, we need to probe it, and we have to test it using the test instruments. So for this frequency tripler measurement, we require one signal generator for the input signal. We require the spectrum analyzer for see the output spectrum. We also require DC sources that we can provide using DC probes. So here is the measured output spectrum of the frequency tripler. We can see here we have the output power of plus 3 dBm at 47 gigahertz, and we can see the reduced unwanted harmonics, and we can here see the conversion loss variation with variation in input power at 15.67 gigahertz. So you can see that for this frequency multiplier, the conversion loss is minimum for a particular power. So this is a very basic characteristics of frequency multipliers. Frequency multipliers are optimized for input power and frequency. So you can see it from here. If you are interested to see the details, you can go to this reference. So now we are going to the frequency quadrupler design from 14.25 to 57 gigahertz for 60 gigahertz application. So this is also designed on the same technology, and this is a single stage MMIC in microstrip configuration. This is also based on common source single FET design. The fabrication is from UMS. The active device used is a single pHEMT of 30 micrometer width and 4 gate fingers. There are nonlinear components of FETs that are used to generate the higher harmonics. These components are nonlinear drain to source current, nonlinear drain to source resistor, nonlinear capacitors including gate to drain, gate to source, and drain to source capacitance. The VD bias is set at 2.5 volt and VG is set near the pinch off to produce the higher order harmonics with good efficiency. If we need to produce the higher order harmonics, we need to drive the device to nonlinearity. So we need to use it in class C mode or class B mode. So class C mode, we will have better efficiency. And the DC power consumption is only 60 milliwatt for this circuit. So we can see here this circuit schematic of the frequency quadrupler. We have the input port at the left. Then we have some DC blocking capacitor C0. This won't allow the bias of the previous stage to come to this stage or leak the bias of this stage to other stages. And we have input matching network and the bias network. Then we have the active device. Then we have output matching network. Then we have some filtering using this stuff, which is actually restricting the twice F0 frequency from the output. Then we have some high pass filter will reduce the lower order harmonics like F0, twice F0, thrice F0, the frequency that is generated from the device. Then we have stability network. The stability network will increase the stability of the device and ensure that the device is not going to oscillate. And finally, we have the output block capacitor. So here we see that it is a very simple design, and we have also some biasing capacitor CB for both VG and VD. These are used for bias stability. These CB are used for low frequency stability, while this stability network is used for in-band high frequency stability. So we can see here the input and output matching networks comprise of microstrip stubs and capacitors. Gate and drain bias networks contain RF bypass capacitor and microstrip stubs. A simple third order high pass LC network is used at the output to suppress the lower order unwanted harmonic frequencies. Then a quarter wave open circuited stub at the twice f0. That is the open circuited stub at twice f0, which will offer a short circuit for the twice f0, but at the fourth order harmonics it will be open, because at fourth order harmonic it will be a half wavelength stub, so it won't affect our desired output frequency. And we have used a series RC network in shunt at the output to improve the high frequency in-band stability. The simulation using ADS by E&ICT Technology has been carried out. The PDK from Foundry has been used for this device and passive component models. The schematic design and evaluation has been done using harmonic balance simulation as the earlier case. And we have EM simulation, we have post simulation, we have stability analysis using S parameter, we have yield analysis for fabrication tolerance that is specified by the foundry. The MMIC chip fabricated from UMS, as we have already seen. The chip size was originally 2.5 mm cross 1.5 mm, but this we have to increase to 3.5 cross 1.5 mm, because as we have seen that the chip needs to be fit in the tiles with other designs of different dimensions, so we need to match the dimension in order to effectively increase the number of designs so that the effective cost can come down. So here is the chip layout that has been simulated. You can see there are plenty of vacant space there, and the simulated output spectrum you can see here. You can see the quadrupler frequency for 0 dBm of input at 14.25 gigahertz. The simulated result says the conversion loss is 3.8 dB, and harmonic rejection is more than 30 dBc. Stability factor is 3.2 from DC to 75 gigahertz. It has to be more than 1, and the yield is more than 93%. And this is the fabricated frequency triplet chip. You can see we have the both RF and DC probes. At the left we have the input RF probe, at the right we have the output RF probe. These are the GSG probe. We have ground pads on both sides of the signal line, and we have the DC probes for VG and VD. This is the measured output spectrum for input signal of 0 dBm. You can see the output power is minus 5.2 dBm, and fractional bandwidth is more than 7%, and harmonic rejection is more than 25 dBc. The measured output power and conversion loss is seen from this graph. We can see saturated output power is minus 4.5 dB for Pin of 0.5 dBm, and conversion loss is 5.2 dB. So here we see the phase noise characteristics of the frequency. We can see here that we have a phase noise at the input frequency, which is a lighter curve, and we have a darker curve for the output frequency as 4th times of the input frequency. So you can see the phase noise is higher at the output frequency. That means phase noise is degraded due to frequency multiplication. And from this data we can see the degradation of phase noise through frequency multiplier. If we see, we can see at every offset frequency the phase is degraded by 12 dB, which is as per the theoretical formula of 20 log base 10 of the frequency multiplication order here. So if we take 20 into log 4, we will get 12 dB. So it is as per the theoretical limit of frequency multiplication. Here we can see that frequency multipliers are degrading the input signal as per the law. We have seen that n square, but again it will produce a better phase noise compared to a single frequency oscillator at 57 gigahertz. So if we can have a frequency source at 14.25 gigahertz and use a frequency quadrupler to produce 57 gigahertz, we can still have better phase noise than a direct 57 gigahertz oscillator. Now we'll see the frequency doubler with integrated output amplifier. So it is a 17.5 gigahertz to 35 gigahertz active frequency doubler with same gallium arsenide based technology. The microstrip based MMIC configuration is cascading two common source pHEMT stages. The first is frequency doubler stage, then we have medium power output amplifier stage. The frequency doubler stage is designed using a single pHEMT of 30 micrometer gate width and 4 gate fingers. We can see the simulation structure here and the simulated output spectrum for 3 dBm of input power at 17.5 gigahertz. We can see here the fundamental frequency, second harmonic frequency, and third harmonic frequency. Our desired output is the second harmonic frequency at 35 gigahertz. The output amplifier stage is designed using a single pHEMT of same dimension. The narrowband response is achieved, and we have class B mode of operation. The impedance matching is achieved by optimizing the bias network and series stubs. You can see the narrowband response here. It is not that much optimized amplifier, but it serves our purpose, so we are okay with that. We have integrated both the doubler stage and the amplifier stage, and the total structure we have simulated, and we can see the simulation structure here. And this is actually the structure of a co-simulation where apart from the device model, everything is coming from the layout simulation. And we can see the output spectrum. The overall simulation result gives us conversion gain of more than 12 dB and an unwanted harmonic rejection of 60 dBc. Stability factor is more than 3.4 and yield is more than 90%. This is the fabricated chip of size 2 cross 1.5 mm. So that is the measured output spectrum for 3 dBm of input power at 17.5 gigahertz. We can see the fundamental frequency suppressed sufficiently. The output power is 12.8 dBm at 35 gigahertz and fundamental rejection is more than 40. We can see here the output power flatness of less than 2 dB from over a 5 gigahertz bandwidth. The maximum conversion gain is 10 dB. Saturated output power is 15 dBm. Phase noise degradation is 6 dB. It is all this 20 log 10 in formula. So this is also as per the theoretical limits, and DC power consumption is 110 milliwatt. Now coming to our last circuit, this is a multi-frequency tripler with integrated output amplifier. This is 15.67 to 47 gigahertz. Whatever we have seen earlier, with that we have another output amplifier stage. So based on the same technology and cascading of two stages, that is frequency tripler stage and output amplifier stage, both are of common source pHEMT based microstrip configuration, and the device dimension is also same. The tripler stage is biased in class C region so that it can enhance the third order harmonic signal power. The lower order unwanted harmonic frequencies are suppressed using single high pass LC filter. Less than 2 dB of conversion loss has been achieved in simulation. Unwanted harmonic rejection is more than 30 dBc. For amplifier stage, we have biased class mode and simulated small signal forward gain is more than 8 dB and return loss is 12 dB. This is also not very optimized, but we are okay with that. This is the total simulation structure that may including tripler and output amplifier stage, and we can see the overall spectrum of the circuit in simulation. The simulation conversion gain is more than 6 dB. Rejection of unwanted harmonics is more than 40 dBc. Stability and yield analysis has been carried out. Impedance matching is accomplished through passing networks and simple microstrip stubs. The unwanted harmonic suppression by narrowband amplifier and 3-element LC filter. That is a very simple filter design. So this is the fabricated chip of dimension 3.5 cross 1.5. Again, we have to increase size a bit to fit it in the tile. You can see the measured output spectrum. The measured result shows a total DC power consumption of 100 milliwatt, output power of 10.3 dBm, and rejection of unwanted harmonics is more than 35 dBc and 40 dBc. Here we can see the variation of output power, and we can also see here the variation of conversion loss and output power with variation in input power. The output power variation is less than 3 dB over 4 GHz bandwidth. Conversion gain is 5 dB. We have saturated output power of 10.5 dBm, and DC power consumption is more than 100 milliwatt. Now, when we have the fabricated, now how we can connect the MMIC to our circuit, because we cannot directly use MMIC or put MMIC in our system, so we need to package it. We'll see that we require bonding of MMIC from system substrate to MMIC. We require a bond. This we will see the effect of bond wires. For high frequency operation, parasitic inductance of bond wires should be taken into account in the simulation. Otherwise, the result of the circuit after the bonding will degrade. The maximum wire, the approximate wire inductance is 0.1 Henry or 0.7 mil dia wire and 0.8 nanohenry for 1 mil wire. This is an approximation. Parasitic inductance can be reduced by using 2 or 3 wires in parallel. However, the mutual inductance reduces the effectiveness of using multiple wires. The maximum current that a gold wire of more than 1 mm length can withstand is around 380 milliampere for 0.7 mil wire and 650 milliampere for 1 mil wire. So for DC connection, we need to take care of how much current the DC will, the bias will draw. If it is drawing more current, then we have to go for gold wire of larger diameter. But we also need to see how is the available space on the MMIC for bonding. If the bond pairs are too small, we cannot use a very high dia wire. That also you have to check. After the bonding, we need to check the quality of bonding using bond pull test to ensure the bond wire's strength. We also need die shear test to ensure the die bond strength. If we are using the MMIC, we are attaching the MMIC on the chip here using some epoxy. So using the die shear test, we need to check whether the MMIC is attached to the MMIC carrier. Now we can also, this is an approximation what we have seen here, the inductance introduced by the bond wire. We can accurately estimate that using HFSS simulation. Here we have simulated the ribbon, one single wire and double wires to see the effect of bonding. Here for a single ribbon of 3 mil cross 0.5 mil, we see that the insertion loss is 0.76 dB at W band, while the return loss is 8.9 dB at W band. Here it will depend on the gap, on the length of the gap. We have kept it 0.1 mm. which is as per the industry standard. And for single wire of 1 mm dia at that same frequency, the insertion loss will increase to 1.6 dB and the return loss is reduced to 5.6 dB. If we use multiple wires, we have better insertion loss of 0.85 dB at W band and return loss of 8.5 dB at W band. So instead of using one wire, we can use two wires, but for using two wires, we require larger bond pads. Whether that is available or not, we have to see. If we do not have, the best thing is to use the gold ribbons for RF connections at the RF in and RF out, and the gold wires are preferred for bias connections, because for bias connection pads are so tiny we cannot use any ribbons. So for DC connections or bias connections, gold wires are preferred. So here we see in actual circuit we have the MMIC that is bonded to the circuit, to the other part of the circuit. At the input and output we have ribbon bonding. For the biasing purpose we have wire bonding. We have also some biasing resistor and capacitor for bias line to suppress the bias related oscillations. And here we can see, and in the middle, the total circuit within this is a MMIC based circuits. We have RF input and output line in microstrip, and the MMIC is sitting at the center. We have connection to RF lines using this RF ribbon bonding. Then we have wire bonding for this DC connections for VG1, VG2, VD1 and VD2. Then the final RF is going from the microstrip to waveguide by microstrip to waveguide transition, because at high frequency at W band we cannot use microstrip or connectors for connecting our circuit to the other components of the system. It will be very lossy. So we have this waveguide input and output for the component, and finally we have the component on the right hand on the right side, and you can see the waveguide flanges for the input and output. This is an example of packaging of W band MMIC amplifier in hybrid integrated circuit module. So we require MMICs and SLCs are attached using conductive epoxy on the circuit. We require gold ribbon and wire bonding for electrical connections, off-chip components for bias stabilization or line filtering, because that cannot be included within the MMIC. In that case, the MMIC size will increase and cost will also increase. So these components are used off-chip, and this quality of epoxy and ribbon or wire bonding are crucial. And use of chip carrier is essential. That means within the circuit, just beneath the MMIC, we require a small block of copper or molybdenum, which will be of same thermal expansion coefficient as that of the MMIC substrate material. Here it is gallium arsenide. So gallium arsenide has got very low thermal expansion coefficient, while the aluminum block has higher thermal expansion coefficient. So if we directly attach our MMIC on the aluminum, due to temperature change, the expansion of aluminum block will be different from that of the MMIC substrate. So there will be a stress generated on the MMIC, and MMIC will eventually crack. So we need to put one block beneath the MMIC like cover, which is also of low thermal expansion coefficient, so which will be the same thermal coefficient as that of the gallium arsenide. So gallium arsenide MMIC won't be cracked, but whatever stress it will generate due to the thermal change, that stress will be generated on the cover block, not on the MMIC. So with that, I conclude my today's talk. If you have any question, I am here.
Sir, there are so till now there are no questions in the Q&A section. So I request the participant to please give their query in the Q&A section related to the presentation.
So whatever question you have regarding the simulation or design, you can ask. And we are carrying out this kind of research and development work at Samir, Kolkata. Actually, our Kolkata center is dedicated for this millimeter wave work. So we are mainly working in the millimeter wave domain. Our other centers like Mumbai center is dedicated for high power application and microwave applications. We have also a center within IIT Guwahati, which is primarily working on tubes, millimeter wave tubes. So if you are interested, you can collaborate with them. You can collaborate with us also. For tech students, we take students for joint guidance. So they can also participate in our lab for carrying out their MTech project from academia. So in that way also we can do collaboration with academia. And it is also not mandatory that you have to stay full time on in our lab. You can also work from your lab. You can do simulation work.
So there are questions in the Q&A box. Are you able to see the Q&A box?
Okay, let me see.
Maybe I can ask them when,
Yeah,
to help you.
please.
So
Yeah,
what about
please.
the, one of them is asking, what about the RF MEMS area? So is there active work in the similar regions in the RF MEMS area?
Yeah, RF MEMS is also you can say this similar kind of domain, but the applications are different. And we have also tested RF MEMS in our lab using the same probe station. And RF MEMS have got their different application like switches. And this is a different actually foundry and different fabrication process. So that is also, but these are not very different. These are similar, but the technology is different.
Okay. The next one is saying, can the frequency multiplier technique be used in the CMOS technology for phase noise improvement?
Yes, sure. People are using CMOS technology for this RF IC application, where they are using silicon-based technology for making many things like frequency multipliers. And in RF IC, you can actually integrate the total transceiver in a single chip. But right now, RFIC is mostly people working on low frequency, like 2.4 gigahertz. There is one program going on called Navik that is for this that is using this RFIC technology. So you can use you can design and develop all of your circuits, including frequency multipliers, for designing and developing your transceiver, and people are using it.
Okay, so the last one is saying, what is the scope for GaN in MMIC based frequency multiplier? Is GaN a better technology than a GaAs?
Yeah, there are difference between these two technology. If we talk about GaN, the basic thing is that in case of GaN, the band gap is higher than gallium arsenide. So when the band gap is higher, we can have higher power. But issue is that the frequency will be limited. So right now, whatever GAN process are available, that is not mature up at very high frequency. So you can have GAN-based frequency multipliers with higher output power at low frequency. But for high frequency application, till now people is working on gallium arsenide for making frequency multipliers. But GAN technology is maturing. Maybe in coming years, at up to W band, GAN will be available.
Okay, yeah, so that's all
And
from the
GAN
Q&A
is
section.
also very costly. GAN process is also very costly, and sometimes getting access to GAN technology is difficult from some external agencies. There are some restrictions sometimes there, because GAN is mostly used for high power and for defense applications. So all these things actually, for any MMIC design, the first thing you have to collaborate with your fab lab, the foundry. You have to keep in touch with the foundry. You have to get all information from the foundry, and based on their feedback, you have to think for which technology you can go for and design your circuit, because sometimes the best technology is not available to us, so it requires on many things.
Yes, sir. So that's all from the chat box, Q&A box.
Okay.
Thank you, sir, for such a informative lecture. So with this, we are coming to the end of the first session for today. So from 11 o'clock, we are going to have the next session. So we are delayed by just 10 minutes. So we will be starting the next session by Aditya, sir. So thank you, Bijit, sir, for joining us. Sir, I request you to please connect us during the validatory session, sir. It's a request.
Okay. When is your validatory?
Sir, it is at 3 p.m., sir, today.
Okay.
Yeah.
Okay.
Thank you, sir.
Thank you. Yeah, thank you to the organizers as well for giving the opportunity. Thank you very much.
Okay. Thank you, sir.
Yes, ma'am. Should I share the slides?
Yes, sir.
Okay.
We have given you the presenter, right, sir? You can share the slides.
Okay, so I think I'll have to share the screen because there's a lot of tool work involved today. So good morning, everyone. Let's see. And thank you, ma'am, for the coordination. And okay, so basically today is the last day for the whole FDP program, and largely the sessions were conducted by Mr. Ashish Jindal from SSPL DRDO, and he gave a very good overview, not just overview, a very in-depth description of different components of a 5G RF chain. What are the different subcomponents, how they are, what are the design implications for them. So even though we do not have a full-fledged RF simulator and PDK like Mr. Bijit was mentioning, but from a research perspective, from a student perspective, we can still look into those things, get better at this area of 5G and RF, and learn a lot of these things from the open source perspective. And he gave a lot, really good understanding for the RF subcomponents. Now, the idea behind today's couple of sessions is we wanted to put it all in a global kind of a perspective. And the way we wanted to do is we wanted to show how does this RF system, so how does this communication link actually look like. So a lot of you might already know this, but a lot of you might not. So the idea is to all put it all in a combined picture. So how do these different components come into play together? So for example, you might have learned how does a PA work, how does an LNA work, how does a matching between two components work. But when you are actually designing a complete chain, so complete link, it's not just a PA and LNA and all the matching that goes and the matching to the antenna, or how do different antennas interact with each other. There's a lot of other considerations which happen as well. So if you're from a communications background, those a lot of that from theory aspect, because you know that you need to put a PLL in the loop, or there are many ways to create a channel. So today what we'll do is we'll look at one brief example for that, just to get a good understanding from the system level perspective. And as I mentioned, this is just one way of doing it. There are a lot of ways to design the similar systems. And the idea here is to understand how do those subcomponents which Ashish described in great detail, how do those come into the picture together? And once you derive the parameters from those, how can you actually build and add those things into a system level simulator aspect? Okay, so what we'll do is in today's session, we will use a very fundamental system level simulator called CPP Sim. And what the simulator does is, sorry, give me a moment here. Yes, so what this system level simulator does is you write all your components in C, models as C. This is also possible to do transistor level simulation, Verilog level simulation, but a lot of these times of large system level models are written in C, C++, and similar languages. And you're able to simulate bigger system level effects, because you cannot simulate the whole chain. Sorry. Yeah, so largely what happens is you have these big system level models. And why are we using, the idea you have to understand here is, why are we using these system level models? And why are we not simulating everything together? The reason is, if you simulate everything together, you'll need terabytes of memory. So to put all the models into perspective up to the transistor level, and if you want to now model all the things in device physics level also, it will take terabytes and terabytes of memory to get that simulation, and it is not a realistic thing. So with the constraints of simulations we have, there is always a hierarchy of simulation. So hierarchy of abstraction, which is put onto your simulation, and you simulate at a given hierarchy level. Okay, so with that view, what we have done is the simulation abstraction, which Ashish showed you, that was one hierarchy view. And if we go slightly above that hierarchy, we now combine those components using their own models, so that we are now able to see how a typical link works. Going into this, before we dive into too much detail, yes.
Your slide is not changing.
Yeah, I did not change any slide.
Okay.
So I just wanted to give a perspective of what we're doing. Okay. And okay, so screen is shared, right, Ashish?
Yes, screen is visible.
Okay, perfect. So going further, before we dive into these outline concepts and actually go into the tool, I want to point out that we will be using a tool called CPP Sim. And in order to use that tool, I think Ashish already held a couple of sessions where he told you how to install that. To make best use of this visualization and everything, you should probably have that tool installed at your end. If not, please try to do it in the background. Today we cannot look at the installation aspect. So to know whether or not that tool runs, what you can do is, there is this, let me close this. So there is something called SU2. If you open SU2 and if you see this window, then your tool is running correctly, and that is what we will be using. Okay, and so coming back to the session, basically, before we go into the tool, I want to give you a bigger picture kind of aspect. What are we doing? Okay, so because this is, if I just dive into the tool and show you just simulation results, you will not be able to appreciate where you were up to yesterday and how does that add up to the overall picture. So means this, I showed this slide in the beginning as well. What we have in a basic RF communication channel is we have a transmitter and we have a receiver, and there is a channel in between. In that channel, what we have is there is a carrier which transfers the data from a transmitter to the receiver. Now, what you have to do is you need to put the data on top of this carrier. So for example, in 5G communication space, this carrier may be a sub 6 gigahertz, around 5 gigahertz signal, or in the 24 gigahertz or 28 gigahertz band. So this is the center frequency. And in this center frequency, what we do is we add a baseband signal. So we add a modulation using some other frequency. So this frequency, for example, in your 4G LTE was 10 megahertz on a single site. So you add a 10 megahertz signal on top of it. So how you add that signal on top of it is done using various techniques, whether it's done using amplitude modulation, frequency modulation, or digital modulation. That's up to the system level specs. It depends on case by case basis. So we will today look at one of those techniques called one of them called a digital modulation technique, and in that digital modulation, we'll look at the Gaussian phase shift keying technique to overview the overall system. Okay, so that is the general context which we are coming from. Now, there are again certain keywords which we have to understand a little better before we actually dive too much into the simulations. So the first keyword, so there are these different ones: center frequency, signal bandwidth, IQ signals, eye diagram, phase noise, spectrum, power, and all these things. So in the next few slides, I will briefly explain all of them to you before we go into the tool environment. Okay. So first of all, going into the general model again. So we have a baseband signal that goes into the modulator. This is our transmitter side, and this creates a modulated signal with a certain frequency, center frequency, and modulation frequency. Passes through the channel. There are losses in the channel. It goes to the demodulator in the receiver, and the receiver demodulates it, gets the carrier out of it, gets the baseband signal, and that is your detected signal. On the transmit side, your signal is at the baseband, your baseband signal, and when you add it on your carrier, then it gets created as mirror images on the plus carrier and minus carrier. So, for example, here this baseband signal might have a bandwidth of say 100 megahertz for a 5G system, and the center frequency might be say 28 gigahertz. So we have a 28 gigahertz signal, which has a bandwidth of 100 megahertz at the center frequency 28 gigahertz. So this WC is your center frequency, and the width of your signal is your bandwidth of the signal. Now, this when I say in the frequency domain, it looks like this. In the time domain, the signal looks something like this. Exactly how do they look in time and frequency domain will vary depending on which modulation technique which we have used. But to put it in general perspective, in time domain, you have some you have some voltages and currents which are changing in time. In frequency domain, you have amplitude with respect to the frequency. Now, when it reaches the receiver again, the receiver gets rid of this carrier and it will again change back to a baseband signal like this. Now, how does this process, this overall process happen? So we need to understand how are we doing this, and where are all those subcomponents which you learned. So are those PA, LNA, where do those fall into the overall picture? That is something which we need to understand in a little more detail. Okay, so first of all, just to give you a perspective, as I mentioned, the The modulation can be of different types. You can have either amplitude modulation. So basically you have a carrier signal, you multiply it with amplitude modulating signal, and you get a output amplitude modulated signal. And similarly, your frequency, you have a baseband signal and you have your carriers, which are just spikes here. And that changes into plus and minus carrier. The baseband shifts to the plus and minus carrier. Now, the idea here is, now we will also look today what happens if this carrier is not a perfect spike, right? It will create issues. So how can we visualize those issues in our simulators? So that we will also try to look at those aspects. Similarly, in phase, you have a modulating signal, which is in ones and zeros, and you multiply it with the carrier, and then you have a carrier modulated signal. How exactly this happens and what are those equations, what are those outputs supposed to look like in time domain? That is diving too much into the communication theory. We do not want to go into the communication theory right now. We'll take a step back and we will look into it from the ASICs perspective. Okay. So next, what I wanted to give you an example before. So before we actually go into the tool environment and overlook the tool environment, this is the last thing which I want to discuss. So what we have is there is this binary baseband data, and this binary baseband data is converted into two signals, I and Q signals. And what do those I and Q signals effectively mean? So a quick example from a QPSK perspective. So if your baseband data in time domain looks like the data on the top here with certain period, your I and Q signals would look like the signals A and B over here. Okay. And so what we have is the in phase first, the first bit gets encoded into A. The second bit gets encoded, which is 1, into B. The third bit goes into A. The fourth bit goes into B. The fifth bit goes into A. Sixth bit goes into B. So the stream of data gets divided into two parts. One bit goes into one stream. The other bit goes into the other stream. So that is what we mean by in phase I in phase and quadrature encoding. So that's just from the example of digital bit streams. From analog perspective, you can visualize it in certain other way, but just a broad description. One other thing I want to create a distinction is we'll be looking today at a QPSK system, GMSK system. So Gaussian shift keying, and what Gaussian shift keying is, effectively you'll see in the system there is a filter, and this Gaussian filter which we put before we pass the waveform into a VCO. So we'll look all this from the tool perspective. I'm just putting it there. So because of that existence of the Gaussian filter, it is called Gaussian shift keying method. Now, so what we'll do first is we'll try to open the tool environment. So let's see. Is the people here are able to open the SU2. So people who are trying to do it along with me, are you able to open this SU2 screen? Someone wants to answer? Okay, so the SU2 screen opens, perfect. Then what we have to do next is so overall in this window, you have these different places where you can load data from. So first of all, what we'll do is we'll try to click on the CPP sim modules. And in the CPP sim modules, what we'll do is we'll go scroll down and search for GMSK module, GMSK example. Try to click on that GMSK example, and you'll see then multiple options. And in these multiple options, we want to click at this overall system. So after you have clicked on this overall system, your screen should look something like this. And I'll wait a minute here so that everyone is able to open your screen and reach this stage, and then I'll explain certain things over here. So just take a minute and reach this stage. Okay, so basically, I'll repeat. What we'll do is, what we did was we went into this, the top right, and this top right option. In this top right option, we found GMSK example. In the GMSK example, we tried to open the GMSK overall system. Okay, that's the one we want. Okay, so if you're able to see this screen, which I'm showing here, let me know, and then Vaishnavi, you should have, otherwise your installation has certain issues. Are you able to see the GMSK example? Okay, so I think, okay, so is there are there students here? So for the students, are other people are able to see the overall system thing? Overall system. So there is some issue with for everyone who is not able to see the overall example, there is certain issues with your installation. So probably a file is missing. And we can you can reinstall it. You can actually follow this session and come back to it. So apart from that, it's not very different. So I'll just explain you what this is going on here. So this GMSK example, what is happening is this is a combination of multiple blocks. And what these multiple blocks are, there is this transmit. There is a transmitter block, GMSK PLL transmitter. So this is this block. We can directly click over here and open this. There, if we go back to the overall system, we have a GMSK receiver, which is called IQ receiver, which we click and opens into like this. And now we go back to the overall system, and there is a simple channel model, and then there are other VCO options. And if we go now into any one of these, right, if we click on say PLL transmitter, then there are other subcomponents also over here, which have been modeled. So what's the way this system has been set up is that each one of these have been written in C++, and these are behavioral models which model our overall system. Now, it is for us, you need to understand now how does it relate to what you were doing a while back is, so everything which you were making, so for example, a power amplifier. So effectively, you can write a behavioral model of that power amplifier, and when you write the behavioral model of that power amplifier, what you do is you describe each and every one of its characteristics. Its gain is its band, or what is its pass band, and everything. It's what is its PAE. And then there are certain other things which you might have alluded to, like the non-idealities associated in the power amplifier. You can put those non-idealities as a behavioral model and then simulate the overall system and see how will it behave. So that's the general idea. Now, even whether or not you are able to see the overall system, if you are not, you can for now just open the PLL transmitter one, and you can work over there. I'll let you know certain changes you can make in certain files and try to simulate it as well. Okay. So I'll go to the overall system for now, and I'll try to show you the general simulation setup. And right now in first session, first we'll go over the general simulation setup, and in the next we'll try to change a bunch of things in there and try to see how it is affecting us and what do those mean from the system level perspective. So and also we what we'll do is, before we do that, we'll actually try to understand what this PLL transmitter and receiver means. So what are these different blocks in here? So before we do all that, I want to just show you how the whole thing actually runs so that you get a general feel for it. And please understand this, that it is up to us that I will only give you a brief introduction today, but this is a very, very, very powerful tool. You can just analyze anything. You can just make models and you can change parameters here. It's CPPSIM also has a very good PLL modeling tool, which you can use to model a lot of behavioral aspects of PLL. So this is a tool which is also used in industry to model a lot of things. So that's why learning this tool and becoming proficient at it is quite advantageous. So what you do next is you go into this tools menu, and there are multiple simulation options, VPP, ngSpice. But today we'll be doing CPP simulation. So we'll click on CPP sim. And after we click on CPP sim, you should get a window which looks something like this. If you do not see exactly the text written here, do not worry. This is because I've run this before. That's why I'm getting certain messages. But for you, you should be able to see some screen which looks like this. So if you click on Tools CPP Simulation, are you able to get this screen? Let me know, please. From any window, you can do it for now, from GMSK, PLL transmitter, or overall system. If you're seeing overall system, do it from there. Okay, so Vaishnavi, if it's giving you an error, then there is definitely, means you are also not seeing the overall system. There's some issue with your simulation setup. So you need to go back to the lecture and slides which Ashish has posted for the installation and try to redo it, a clean installation. And you can also go on the website. I think there are certain system level. So sometimes it does not run well on a 32-bit system and stuff like that. You can try to figure it out. And today, because it's a short couple of hours session, you can just follow along and try to understand things. Okay, so I hope people are able to see the screen. And if you're able to see the screen, I want to explain certain things over here. So our simulation mode here is CPP Sim. It has also extensions to MATLAB and Simulink, which we'll not explore today. Just wanted to point that out. What you do here is you go and click on this edit sim file. And for now, you just open it and then press X. So you click on edit sim file and press X. And after that, you should be able to get a message here that sim file is test.par. So whatever the name of this file is, test.par, should show up here, your sim file name. So please do that. Click on edit sim file. A file would show up. And then you just, for now, just close it. We'll understand what here exists later on. And for now, let me make it this thing as one, because you don't have to do this change. This is just for me. So a file, you click on edit sim file, a file looking like this opens up and you close it, and a sim file option shows up over here which says test.pr. So does this work for you guys? Can someone confirm you're able to do this? Okay, nice. Just I'll give another minute for everyone to just do this. And if you have done this, what you do is you click on this compile and run option, and this will run your simulation. And after running, once it reaches 100%, please let me know. So the message like I am getting, you should be able to get this message. So let me know when someone is able to finish the simulation. The simulation time will vary depending on your system specifications. So whether you have a 16 gigs of RAM or 4 gigs of RAM, it will take slightly different time. So your compile and run should get completed successfully, basically. Okay, so one of you guys have been done. So I'll just give you 2 minutes for everyone to catch up and finish this compile and run, and then we'll see how we actually visualize this. And before we actually go on and understanding the system, I just wanted to make sure everyone is on the same page and is able to at least run one thing. So Hasim, what you do is you click on this edit sim file and something opens and you just close it for now. In the sim file, you will see this test.par written now. And after that, all you have to do is click on this compile and run. So I'll give a minute here for everyone to catch up and finish this. So I see there are what 200. Okay, so good, Wasim. Basically, there are a lot of participants here today, and I'm seeing only 4 or 5 people are replying. So what's going on? By now, everyone has stopped worrying about the simulation aspects. Okay, so I'll proceed further, and what we have to do next is you go and search for CPP sim view. So if everything runs correctly, this file window would open, which looks like this. So CPP sim view. So it opens multiple tabs. And if you are able to open this CPP sim view, then it means your installation is correct and your run actually ran correctly. And in the first option, you should see test.par written. So if you click on this button over here, it will say test.par. So if you're seeing this, let me know. Anyone apart from Aditya Kumar is able to see this? Okay, nice. What you have to do next is just click on the next button over here. For now, it says test spectrum. You go and just click on test.tro for now. So Suresh, either your simulation did not run correct or some issue with your installation. So yeah, you'll have to just follow along for now. Right now, because we have just one session of this, we cannot actively debug CPP sim issues. Yeah, I mean, you can install anywhere. I don't think that's the installation drive is an issue. So what you do, guys, next is you click on this test TRO and the second button and select test.tro. And then there's this no nodes written thing, the third button. You go and click over there, and then you'll see a bunch of output signals over here. So Gaurav, are you running from overall system or are you running from the the transmitter. So overall system. So I'll tell you where this test spectrum and test comes from, and later on you can actually modify these files yourself to make this run. Okay. So basically, one of the tests is running. So on the second button, you select the test TROs. In the third, what you say, you have these you should be able to see a bunch of these output waveforms. And what you do is, for now, you just click on any one of them and you see a certain waveform. And in the next one, you see another waveform, and the next one, you are able to plot another waveform. So right now, you are getting certain waveforms here. And what we need to understand why we are not, there is nothing coming over here. Okay. So for your case, what might be happening is you might be getting a lot of signals over here. So why is my signal not coming? So one of my parameters is different. And the parameter which is different is I have not enabled the model. So I have not enabled the transmitter model. So if I do this, if I change it, and if I press save, and if I go here and do a compile and run again, I'll explain what is happening, just trying to show that how you play around with the tool right now. Okay. So explanation of what these models mean, what this transmitter side mean, what this receiver side means, we'll go and look at that. So now we go back to the CPP sim view. We go to the files, we go here. Now if we plot, now we do reset note list, sync this, and okay, so for me, it's not working right now. I need to see why the output file is not simulating. So test arrow. Okay, so this is not giving the output. I'll check this. So I'll come back to this. You should be able to get a waveform, which is a time domain waveform over here. So let me, in the 15 minutes break, I'll fix this. But coming back to now what we are doing. Okay, so that was just a brief introduction, how you run simulations and how you plot them. But coming back to the, yes, means for everyone, they should be coming. You should be able to see a bunch of waveforms. That's fine. I think I have put certain settings in there, just trying to do certain complex simulations, which is causing it to not have the outputs, but overall it should run. That should fine. Yes, perfect. I think everyone should be able to get this. That's fine. So very nice. So before we take a break, I wanted to give an introduction as to what the overall system in the CPP sim is, what we are simulating. Okay. And then we will go back after the break and look at that system again in the CPP sim view and try to understand what is going on. Okay. So let's see, we'll go into the full screen mode and okay. So what we are simulating is I'll tell you, Gaurav, I'll tell you a few things in the simulation aspect also. You can play around with the waveforms. So I'll get back to that. So what now to understand what kind of RF system are we simulating? Okay. Before you try to analyze, the goal of this talk today is not to just tell you how to run a tool. The goal of the talk is to how do you run an RF millimeter wave system analysis on that tool as well. Okay, so you need to understand what you are simulating there before you actually play around with it and just so that you're not just clicking random things over there. Okay, so understanding what we are doing is on the transmit side, what you always have some kind of a reference signal. So the reference signal is, for example, used for a PLL to be in a sync. So sometimes these reference signals are generated using crystal oscillators or something in that effect. Okay. So that reference signal is now used for in a PLL loop, which is on top, and also on IQ generation signal. So reference signal is used for both the PLL and the IQ generation. Why do we have a PLL and why do we have IQ generation now? So the reason we have IQ generation is because we have some data generator block, which is using our reference signal. The frequency of this data generator block is not the same as our IQ signal. So its frequency is 5 megahertz in our simulations, but the reference frequency is higher. So we have a reference frequency which is going into the data generator and also onto a PLL loop. That data generator generates a signal which looks something like this, ones and zeros. Now here -1 and 1 basically, but effectively ones and zero encoding. That signal goes into a filter, a Gaussian filter, which encodes it into which passes it through a low pass filter, and then it encodes a phase encoding on top of it. You have cos, so I and Q signals out of it, and then you pass it through a D to A converter, and now you have analog waveforms, and those analog waveforms go into the I and Q multipliers of your PLL loop. Now, first of all, why D2A converters? Because your overall PLL loop here is analog and you're transmitting an analog signal. And the other question which might arise is how are we actually designing all these components? So all these components in your current simulator are written in C++. Okay, so everything has been written in C++. So that's your current status of things. Now, in your current status of things on the top over here, what you have is you have your PLL loop. Your typical PLL loop comprises of a phase frequency detector, a charge pump, a loop filter, a VCO, and the VCO provides signals into an INQ generator, which multiplies the INQ signals to the VCO frequency. And then if you put that into a loop based on what your signal bandwidth is and what your PLL bandwidth is, you get certain output waveform over here. And basically you're passing, you need to understand it from a very top level perspective. These INQ signals, you're encoding on top of your carrier. Carrier is generated by your VCO. So VCO generates a 900 megahertz signal. You put a 5 megahertz signals on top of it. So what happens, as we discussed before, your baseband is now shifted to your FRF, right? And your baseband goes over here. And how are we generating this? We are generating it using a power amp. So till now, all and everything your model was this power amp, right? Now we are seeing how does the power amp actually get that signal? So there is this huge signal chain which is associated with that before that power amp to actually get that signal. From your perspective, you also know now what are the issues with this power amp, so you can actually model this power amp better, right? From other system level issues are like there is a noise in this RF band, so that these noise are associated due to various reasons. There will be a VCO noise, there will be noise due to each of these components, there will be noise due to this power amp. So that is also modeled in your current RF system setup. So that is the system setup from the transmit side. From the receive side, what you have is you take the signal, you pass it through a band select. So what does a band select signal do? It gets rid of these undesired interference things. So it selects only the receive band. And in that receive band, then you select the channel where you actually have your information. And then you pass it through another multiplier. Now what this multiplier does, it converts it back into the baseband. So from FRF, now you transfer that. From FRF, you go back to your baseband. So your signal is now in the centered around 0. Since now it is in low frequencies, you can actually look at it. You can actually put ADC on it and do all the other things. So here we have added now on top of the signal, what you have added the transmit and receive noise on top of it. So that is another system level issue. Okay. So this transmit and receive noise are added. So this is the general setup. From the transmit side, you have a VCO, a PLL loop, and IQ signals get multiplied transfer from baseband to an RF band. RF band gets transmitted. On the receive side, you have your RF signal with the baseband information modulated on top of it. You pass it through a bunch of filters. You pass it through a mixer and get your baseband signal back. So that is your overall PX-RX chain. Now there are multiple components associated in that PX-RX chain, some of which you modeled in great detail, like PA, LNA, mix, some aspects of matching associated with them, and certain filters. But the overall system is a lot more complex than that. And when you are simulating overall system, you need to put an abstraction on top of it. Here we have put an abstraction of and modeled it using C++, and we are more simulating that system. Okay, so that is the overall setup. So from the simulation aspect, we have a lot of issues like non-idealities and how do we add different other models on top of it. So we'll look at what is the different possibilities here. But this is the general setup. And if we go back to the CPP sim, and if I go into the GMSK transmitter, we'll go and look at these components and whether they match with what we discussed in our presentation. But yeah, we'll go into each one of these details in slightly more detail for each one of them, what everything does. But before that, I'll take questions now. Okay, so if anyone has any questions with respect to what we are discussing. So with respect to the overview of why we are doing what we are doing today, if people are not able to follow, please ask me. Context-wise, if everyone understands what we are doing, why we are doing what we are simulating in an RF system. So we can dive into these simulations. That's actually the easier part, but you guys need to understand what we are doing. So if you do not understand what we are doing, then it'll be a big issue. So Madan, these files are actually available in the CPP sim download place. There are a bunch of download directories that you can go and find that. That should be easy. Otherwise, late after this session, we can post them in the drive as well. Okay, that's a nice question, Wasim. Why the band select filter before the LNA? So typically, filtering is done in multiple stages. So the reason so the way a typical RF channel works is so you have your carrier, and say in 4G LTE, the carrier is 1.8 gigahertz. And then there'll be another carrier which is at 1.85 gigahertz and 1.9 gigahertz, and you'll have different 10 megahertz bands associated with them. So these different carriers at 1.8, 1.85, and so on, these are your channels. So you have you do not just pass information at one frequency to everything. So everyone gets there are multiple channels. So you have to so effectively where your information exists, you deselect their channel using this channel select filter. So that is after LNA. But before even doing that, this whole band, so say starting from 1.8 gigahertz to 2 gigahertz where your 4G LTE might exist, you have to select that whole band. Why do you select that whole band? Is typically what people use is something like a SAW filter, surface acoustic wave filter. So what they are, you put them as a band select filter before your LNA because there are huge interference sources, huge noise sources. If you do not cut them off, your system would not work. So that's why. Now, what can these interference sources might be, right? So if you have communication at 1.8 gigahertz, your Wi-Fi might be running at 3 something gigahertz, and you might have other communication going on, and so there are huge interference sources which you need to get rid of. That's why you have a preliminary band pass filter. Skantamani Sundarajan, yes, you can do using ADS for sure. But the point is you need to have ADS to do that. So what we are trying to show here is from open source perspective, if you do not have paid tools, how do you do this? How do you learn the aspects of 5G and RF without actually having to pay for huge tool and PDK costs and foundry costs and stuff like that. As students and researchers, how can we make use of the open source environment for the same? ADS, you can for sure do anything. It's a brilliant tool. Okay, any other questions? ADS is so you need to understand there is no concept of PDK in a system level model, Aditya. So PDK is associated at the device level, right, or transistor level. So here we are doing system level modeling. We are writing what we want to simulate. Okay. So if there are no questions, I think it would be good to take a 15-minute break right now and get us back on track. I kept it a little fast to give you a complete overview of what we are going to do. Next, in the next session, we will take a look at complete simulations. We'll try to simulate a bunch of cases.
Okay, thank you, sir. So we will break for 15 minutes. So we will be joining back by 12:15. There is an important announcement for all the participants. Today we are having the validatory session. The validatory session will be from 3 p.m. So please connect us for the validatory session. And there is another announcement for the participant. From 12 o'clock, the feedback link will be live. It is already available in the drive where we share with you the notification. So I request you all to please click the feedback link and give us the valuable feedback so that we can improve ourselves. Your suggestions will help us for improvement. So I request you all to please give us the feedback by the link which has been provided in the notification section. So thank you. With this, we will be breaking for 15 minutes. We will join back by 12:15 and the feedback link will be active up to 3 p.m. So please give your feedback up to 3 p.m. Thank you.
Okay, ma'am, should we start?
Yes, sir, we can start. Yeah, we can start, sir. It's 12:15.
Okay, nice. So now I wanted to give you a little more understanding of our simulation, what we are simulating. So if you have the overall system, it's fine. If you don't, just try to understand what I'm trying to explain over here. So we have a transmitter and we have a channel and then we have a receiver. On the transmitter, we are only transmitting the I out signal from the. If we go into here, we have these signals, these I out and Q out signals, and but we are only transmitting the signal from the VCO right now. So that's why we are only transmitting the I out signal. So if you do not understand this, it's because the I and Q signals have been passed through the VCO into a phase log loop, and that's why we are only looking at one of the signals which goes into the channel. So you can accept it for now. But the other aspect which you need to understand is the output of the VCO is what we care about as the transmitter output. If we go back up one hierarchy, so how am I diving into the hierarchy? I'm just clicking on it and pressing E, small e, not capital E. So if I go click on it and press E, I'll see this. You use MATLAB. MATLAB is a paid software. The fact that everyone pirates it and gets it for free doesn't mean that it's a free software. Or you have it in the university, but it's actually from industry perspective, it's a really expensive software. Okay, so you need to understand this is one thing which is missing in the Indian education and Indian industry environment. Also, the fact that you can pirate something doesn't mean that you're getting it for free. So we need to stop this practice. And the fact that we have it available in the academic environment doesn't mean that it is available in the industrial environment all both ways. So not every company is a big company. Not every company is Intel, which is going to provide you with big fancy softwares. If you're working in a new cutting edge startup, you need to sometimes make use of what you can. So just from that perspective, and also we should not pirate, basically. I'm pretty sure no one here has bought a personal license of MATLAB for 2 lakhs or something like that. Coming back to what we have is on the transmit side, we have a similar setup. We have these, we have this IQ generation thing, and this IQ generation thing is going into the PLL loop, and this PLL loop is the same thing. We have a 100 megahertz reference, PFD, charge pump, and that charge pump, and then low pass filter, and then a VCO. VCO output is going out. From our perspective, what we'll observe is this I out for the VCO, which goes into a channel. Our channel is currently just modeled as something which is lossy, a 1/5 gain. This thing goes into the receiver side. The receiver is again just takes the I in, and then the pass. We are adding noise on top of it to model the actual noise, and then it passes through to I and Q inputs of another frequency reference, right? So we get I and Q inputs, and then you pass it through a series of filters. Now, if we, instead of pressing E, if I just double click on this, I am able to adjust a lot of things over here. So as we simulate, we'll try to change a few of these parameters and also try to understand what they are actually doing. The next thing in this test bench over here, what we have is this VCO quadrature. So what this is modeling our frequency source on the receiver side. Control E, Aditya, control E. E is to dive in, control E is to go back. Okay, so what we have next is at the bottom here is you can ignore this constant for a while. This is just to start. This is the control voltage of the VCO. But the VCO quadrature, we have a quadrature VCO, which this is the frequency source for our receiver. Now, if you'll see here, we have put the center frequency as 900 megahertz. There is certain AVCO associated with it. Reason is it's not important right now, but you can use this VCO for other purposes. For example, if I go and actually dive in here, we have a VCO here where the KVCO was something different, right? You can use the VCO with at other places as well. So then the last point here is this phase adjustment, right? This is 305 degrees. So we actually need to understand why is this phase value there and what has not been modeled. So we are getting this phase value from somewhere. So what does that mean? We need to understand this. Okay, so we'll look into that as well. So that is a brief explanation of the overall test bench. Now what we'll do is, now if I go back and into this menu, what we'll see is if I click on this edit sim file, it is saying number of sim steps as certain value. It might be 1 in your case, and we'll see what is the effect of increasing or decreasing this is. Then the next one is first it's saying output test. So if you remember, I was saying you get two outputs, test and test spectrum. That's because of this reason. So test is you're creating two outputs here. The first output is this test output, which has the trigger as this clock in the internally. Trigger is just the start signal, and then you're only probing these signals. So you're probing inside XI1. XI1 is your transmitter. It's labeled there. And you're looking at XI1, ISIG, QSIG, and then few other signals over here. Okay, and then the next what's happening is you are actually, what you do is you run this for a while, and then after that you run another test called test spectrum. We will also see why we actually want to look at this test spectrum. Okay, so we'll come back to this thing. So, but overall, since your test file has written two tests in it, that's why you are getting two tests over there. So whatever you write in here, that is what effectively your test is going to run as. So this is where you specify everything about what your test is supposed to be. Okay. So after I press compile and run, my code runs, and the faster it runs depends on how many simulation steps I've put in there. Okay. So if it runs faster for your case for right now, because you have number of simulation steps as 1 to 10 to the power 6, and I have 10 to times 10 to the power 6 basically. So I will let it run. And in the meantime, if you have questions with what we are discussing with the overall setup, please feel free to ask in the Q&A box. Firozanam, I think this question is for you. This is not opening. I think this is with reference to the review form.
Yeah, sure, sir. We will check. I think so. The link is open. Then also we will check.
Okay, so this is about to finish, and After this finishes, we'll go back to the CPP sim view. And in the CPP sim view, we'll do sync, load, so sync, test parameter, test TRO nodes. And I just reset node list to get rid of the old thing, so this will go away. And now if I do I filter and Q filter, okay, so these are the signals. So what are these signals? If we go and reference it back to the naming convention in the schematics, these are the signals which are received by our receiver side. So these are decoded signals which are received by our receiver. So in terms of the schematics, these are I and Q signals which the receiver thinks we are sending. Okay, so these are those I and Q signals. And so the reason I'm going fast is because I had already shown you that you can plot these. So I'm hoping people are able to actually plot these. So I will actually wait 5 minutes after I've covered something to actually see if people are able to plot these. Okay. The other signals which you can plot is ISIG and, sorry, going back, QSIG. So what these are signals from the transmit side. Okay. So one thing you'll notice is the signal strength from the transmit side to receive side is roughly 1/10. And the reason is the gain loss in the channel. So whatever, basically it's power versus voltage kind of thing. So right now the loss is 2 times. And apart from that, your I filter is same as ISIG, and your Q filter is same as your QSIG. It's actually, there is some issue in the QSIG. We will need to check this, but there might be delay associated with this. But overall, we are getting the signals and they are attenuated. And what we need to do is, the question which comes is, the question which comes up now is, how do we actually understand whether our link is working correctly or not? So all this plotting is all well and good, right? You're just simulating something, but from the link perspective, how do we actually characterize it? Okay, how do we say whether with this transmitter property and with this receiver property, will my link actually work? So how do we classify that whether my link will work, kind of thing? Okay, so classifying that whether my link will work or not, there are certain parameters for that. And one of the parameters is bit error rate. And in order to characterize bit error rate, the term which is used is I diagram. So people overlap multiple cycles of your signals, and based on those multiple cycles, you plot your I diagram. So what we'll do is we will try to plot I diagram and see how our signals actually look like. So is our signal looking good enough? Are we decoding it correctly on the receive side? Is our I diagram clean, both on the transmit and receive side? And then varying different system properties, will they change? So one of the parameters which we'll use to analyze this system is this I diagram aspect. Okay. So this is slightly complex on how you do it in CPP sim view. So please follow along as I tell you. So you go into this plot sig. In this plot sig, what you do is you go and search for this ISIG. Okay, in this ISIG, if you actually double click on this and based on the version of CPP sim you have, it might open a pop-up window. Or if it does not, what you can do is you can just go and type here directly. So here you can actually just type anything. Okay, so it's possible for you to type on the bottom here. What you want to type is exactly what I have written here. So you would be getting X times period or something like that. So the period thing you need to substitute to 2/0, 2/0 dot 5E6. So we are specifying the period here. So, and the 2 is because we want to take 2 symbols in our I diagram. And then the next one is 5E minus 6. We will come back to why we have that as well. And then the nodes. So nodes is the information it will pick up from which node we want to plot. So try to specify this information in the CPP sim view, in the ISIG. So find the ISIG, try to specify this x comma 2/0 2/0 dot 5e6 comma 5e minus 6. So in that, please pass that argument. And once you are done, you go back into the nodes and then you click on any one of these and you should be able to see a waveform which looks like this. But I will leave this window up and this window up for everyone to try and do this. Okay, so try to pass this and click on any one of the signals and let me know if you're able to get an eye diagram. So yes, take 5 odd minutes here. Try to get this done. Take 3 or 4 minutes, people. Everyone, I want anyone who is able to simulate to catch up to this point because we'll do a bunch of analysis based on this. Can someone else confirm if they're able to get this? Let's wait till 12:35 for everyone to catch up to this. So ISIG needs to be changed to this, and then you click on nodes and get back to this. Any signal, you'll be able to plot eye diagrams which look like this, basically. So if your nodes are not there, then you might have had an issue in the simulation, Tachi. Tachni. Sorry, I'm not pronouncing your name correctly. Try to resimulate, and also in this file, in the edit sim file, make sure that in the probe there are these nodes written. Make sure that the names of nodes are written. If not, then we'll need to fix that as well. So yeah, guys, take a couple of minutes more and try to get this done. Have an eye diagram so that you're able to better visualize the rest of the session. Okay, it seems only 2 or 3 people are actually doing it, or people are still doing this or trying to get this done. Can someone tell me so that I can actually move at the correct pace? So if your system's installation is not correct, then you'll have to redo it later. But if your installation is running correctly, please let me know in the Q&A once you're able to finish things. Or if you're still doing, let me know as well. Okay, so I am assuming people have been able to do this, and so if you have been able to do this, then what I did was I plotted the eye diagrams for all of these. The input side signals and output side signals. So the eye diagrams, what they look like are these. So in the eye diagram also, you can see that the signal amplitude has gone down from the transmit side to the receive side. And the other thing you can notice is that both eyes are associated with a given horizontal and vertical opening. And based on what your given horizontal and vertical opening is, you can characterize your system based on that. Okay. So there is this parameter here, right? In our overall transmit set TXRX setup, there is this parameter called this phase adjustment, right? 305 degrees. Now, the question is, what does this mean, first of all? So if we go back to our eye, and we are transmitting certain signal, and we are transmitting the signal at the bottom. It goes through our channel and has certain loss. Now, the transmit VCO and the receive VCO are not on the same. The transmit VCO and the receive VCO are not in sync, right? So what do I mean by that? So, for example, how are we going to know when to sample for a data at the receiver? So the receiver has to have certain information about what is the phase of the transmitter to be able to figure out where to sample in this eye, right? If I sample in this receive side, if I sample the eye at this point, then there is no piece of information present here, right? You cannot decode whether it's a 0 or a 1. So you need to, the idea for the designer is always to be able to figure out, they want to sample at the center of the eye. So wherever there is the highest vertical and horizontal opening, wherever the eye opening is the biggest, you want to try to sample at that point. In order to try to sample at that point, now you need to determine where exactly is that sampling point. And what has not been shown in this setup over here is the fact that your sampling point has been empirically determined as 305 degrees. Okay, so your phase on the receiver has been determined as 305 degrees empirically, but in an overall receive channel, there is a whole closed loop in itself. So there is you take this IFILT and QFILT data, you pass them through ADCs, then you try to get this phase information out of it, and that's how you know where to sample in the receiver as well. So that part of information is missing. So if I actually go and change it to, I take out the 0, right? If I make it 35 degrees, okay. Now I save this, and now I go and actually run this again. Okay, and let's see what will happen. While this runs, if anyone has any questions, you can ask me. Aditya, asynchronous, so it's a synchronous on the transmit side and synchronous on the receive side. And you transmit the clock with your data basically. So because your clock is encoded in your data and the receive side, because of a feedback PLL kind of loop, you are able to figure out what your transmit side clock phase was and you pass that information back to your receiver. So it's not exactly an asynchronous system. Kachni, if no output files, no nodes, then your simulation is not running correctly. There is some issue. Or installation or some, there is some issue, means we cannot debug it in this live session. Okay, so this ran, and now what we can do is we go back to this, we say sync, this, we reset our node list, and then we plot this IFILT and IFILT again. So I do not know if you are able to see this, but your overall eye diagram has deteriorated from previous iteration, and you are getting a lot less cleaner eye basically. So your phase adjustment has an effect on the overall eye diagram. Then the next thing which I want to actually go back to the slides to explain this. And what we want to look at is a few things. So first of all, first thing which we want to look at is a few non-idealities, right? So what non-idealities can we actually analyze using our current setup? And then I'll briefly overview as to what can you add, what can you add as researchers and students on top of this system, which based on what Ashish has already taught you. Okay, so to understand the whole picture, you need to understand what has been modeled and what is missing. So we'll look into those aspects as well. So first of all, non-ideality wise, I want to quickly explain two concepts here. So intersymbol interference and phase noise. So starting with the second one, phase noise. The small diagram at the bottom of the screen, okay, what this shows is that you instead of a given a peak, so at your center frequency, your carrier is not just a straight line, but a distributed. Your energy is distributed across a bandwidth from the carrier. So you basically your carrier is not perfect. Okay, so Mr. Bijit in the previous session actually showed you actual measurements of this, right? And you saw what phase noise characteristics look like. So basically your carrier is not perfect. You need to understand that. That adds noise. So we will try to add few noise sources and see what our characteristics look like. Okay. The second thing which comes to picture is this intersymbol interference. So when does intersymbol interference come into the picture is cases like this. Okay, so on the top, if you have a signal, like a perfect signal, and you pass it through a low pass filter, it effectively looks like what we have on the right. Right now, if you take that signal and you further you pass it through another worst low pass filter, then it would further end up looking like this. Right. So based on what your low pass bandwidth is, your different symbols, your ones will try to go towards zeros, and your zeros will look like ones. So you're not able to clearly distinguish between different symbols. Okay, so that is the issue which happens based on your low pass bandwidth. and also in your current system based on the PLL bandwidth. So same things you can observe from your test setup. What you can do is, say I make this again 305. And now, for example, I change my receive side FP to, so this FP is my low pass bandwidth. Okay, so what is my FP? My receiver low pass bandwidth. So I make this, for example, 250, or let's make it 200 kilohertz. Okay. So if I make it 200 kilohertz from 2 megahertz, 10 times decrease. And if I rerun the simulations, right? So let me get rid of this thing. I save this, I go to this, I here, and I compile and run. And let's see what will happen if I change my receive site bandwidth. So you should also, now that I'm running this, please try to do it on your end as well. Try to change the receive site bandwidth, filter bandwidth, cutoff frequency, and we'll now together see in the eye diagram what is the effect. So if your simulation finishes before mine, you need to tell me what will be the effect. And if you're not running the simulation, can someone want to judge what will be the effect in the eye diagram for change if I make the receiver low pass bandwidth as 200 kilohertz from 2 megahertz? Anyone wants to take any guesses? No one wants to guess what might happen to our eye diagram if I deteriorate if there is intersymbol interference. Basically, ones are looking like zeros and zeros are looking like one. So, Aditya, why do you think there'll be more opening? So if ones are going towards zeros and zeros are going towards ones, you got more opening? Shouldn't you get lesser opening? Yes. Hopefully you got lesser opening, otherwise something is wrong in our setup or we are simulating something incorrect. Conceptually, you should get less opening. Rupa is right. So let's see. ISIG is correctly selected. And if I plot this, okay, so what does my signal look like? You can see that pretty much everything there, you barely have an eye here, right? And why is this happening? So Anurupa, you're right, there is more noise, but where is that noise coming from, right? That is the question. That noise is right now originating because your receive side filter bandwidth is not correct. If it is not big enough, so it is leading to us making decisions of ones like zeros, and zeros are looking like ones. We have really deteriorated our signal because our our low pass filter bandwidth was not correct. So Wasim, just to quickly review, ISIG is selected from this button, just a second last button. And there you select ISIG. In ISIG, you pass these values. And then you go back to nodes and you select the node where you want to plot. To put another thing in perspective, you need to understand your transmit side is still good. Okay. Your transmit side is still sending the correct data, but the fact that your receiver low pass bandwidth is so small, your cutoff frequency is so small, that you're not actually sampling it correctly, or your eye doesn't have the correct opening, right? Does this make sense to everyone? Everyone is able to understand this? Any questions on this? I will wait for 2-3 minutes over here so that people are able to catch up to this point. And by reducing the receiver bandwidth, they're able to get a deteriorated eye. So I'll wait at this point. Let's wait till 12:55 and then for everyone to catch up. Anurupa, threshold is different. So threshold, basically the effect is like this, right? So if it's because your bandwidth was so small that you did not let the signal rise to 1. It took it forever to rise to 1, and before that, if another 0 happened, then it did not reach to 0. So because that's why your signals are not going fully up and down, because they're taking very long time. Because they're taking very long time now, since they're not going fully to up and 0 and 1, that's why your zeros are looking like ones are looking closer to 0, and your eye width is decreasing, or eye height is decreasing. So yes, let everyone catch up to this point. Take another 3-4 minutes. So Mahashweta, all you have to do is change this FP from 2E6 to 200 E3. So from 2 megahertz to 200 kilohertz, decrease it by 10 times. And then resimulate and then replot everything. Close your CPP sim view and plot again. So Vijaya, you need to pass this. So in ISIG, make sure that this is written. So instead of period, you need to write 2/0.5E6. You can later on change these parameters and figure out why, because effectively this says this is 2 period symbols for your the eye diagram, and your period is 5 megahertz. So pass this to 2/0.5E6 and then comma 5E-6 for the next parameter. Once you pass that, this is the number. You can just double type over here at the bottom. Then you click on the correct node. Okay, so is someone able to see a smaller bandwidth? Sorry, a smaller eye diagram opening. Someone reach that stage? Let me know. Then we'll proceed further. First, let people catch up, because this is important. Nice, Gaurav. Okay, so yeah, no one's been able to reach this stage. So I'll let you simulate at your end. Let me know how it's going. So what I'll do is I'll change this thing back to E6 and the receiver side bandwidth. And what we'll do is we will change the PLL bandwidth to now 200 kilohertz. Okay, so let's see what is the effect if we change the transmit side bandwidth. Okay, so we'll change the transmit size bandwidth now. Just for clarity, I'll close my CPP view and then I'll save and compile and run and see what happens. So for everyone who is following along, okay. So what did that do? Yeah, okay. So rechange your receiver bandwidth to 2 megahertz and then change your PLL bandwidth to now 200 kilohertz and see what's going to happen. And then compile and run. Now, and then plot both transmit and receive side eyes and see what is the difference you see based before. You were seeing the transmit size side eye was clean, but receive side was closed. What do you observe now? Someone needs to tell me. Yes, I'll wait here till someone tells me what's going to happen. So if someone's simulating, you should be able to simulate this. I'm just asking you to rechange the receiver low pass bandwidth to cut off to 2 megahertz back, and then the transmit one now, PLL bandwidth goes to 200 kilohertz. Q&A box, answer, come on, someone needs to answer this. Okay, so I don't know what previous results means, and Gaurav saying you're getting more opening. So let's see what happens on my side. The transmit, this nodes, I say this. Now I plot the transmit side, which is this, and my receive side, which is this. Okay, so yeah, so the eye improved, but since my there was aliasing induced due to my transmit side, that my receive side was not able to correctly filter it out. So yes, your observations are same as my observation. Absolutely perfect. So this what we are visualizing here right now is what this is a time domain visualization basically. So we are visualizing everything on the time domain. So by eye diagram visualizations are time domain visualization. Now similar visualization you can do in the frequency domain side. Okay, so what you do is basically your power spectrum density is a measure of how good your signal strength is in the in your receiver, in your PXR exchange. and you can plot that, your power. So the way you plot that here is there is an option given where it says plot PLL mod, this option. Okay. So next we are going to try to explore this option. Okay. This is the PLL modulated spectrum plot. And the only thing you need to now change here is this 5e minus 6. You need to change this option. Okay. So try to change this option 5e6, sorry, 5 not 5e minus 6, 5e6. Pass this option and basically 5 megahertz bandwidth. And then what means I'll get back to this, and then we go to nodes and we click on this. What did I click on? I clicked on this filter out. There is this filter out option. I clicked on this and I got a plot which looks something like this. So try doing this and tell me if you get a plot which is looking like this. Okay, so I'll leave these up. So in the PLL mod spectrum, pass 5e6, and then in the nodes, select this. So Aditya, are you getting a plot which looks exactly like this, or it is not exactly with the same granularity or different or something else? Okay, nice. Nice. So if people do not get exactly same or get certain distortions, what might be the reason is in the sim file here, your simulation steps. So you're not having good granularity in your simulation. So when you plot that data in frequency domain, you do not have enough points to plot a frequency domain plot. So this is a typical thing which always keeps happening when you try to convert time domain data into frequency domain. You need to have enough points in your simulation. So here what you do is you can go to the sim file, you can edit it and make it 50 or 60, something like that, based on whatever your PC can realistically do, because the more you do, it will be harder on your PC. So for example, I put 60 over here and I save this, and what I'll do is, for everyone trying to plot it, I will leave this up. How this thing. So I'll leave this up, and so that you can put the correct formula in, and then in the parallel I'll run this. Now this is going to take a while, so this will take 5 minutes, and you should also try to do it on your end, and then we'll see what is the effect on the spectrum density plot. Hey everyone, so if you are not able to run this in your laptops, you can run it at 20, 30 or something like that, instead of 60 or 50 what I am putting. So if this is not run for you, then you can actually run it on the smaller number of time steps. So I'm just trying to run it to show what is the effect of increasing the number of time steps. Try it if you can run. In the meantime, this runs. We'll see how the plot comes. If anyone has any questions, feel free to ask right now. We can make use of the time. And for everyone in the background, you should try and run this. So is anyone running this in the background, or am I just the only one running this? Any questions by anyone? Or everyone wants this course to now just everyone wants this course to just get over. Facility to fabricate the multipliers. So you're talking about the multipliers Mr. Vijit talked about. So I am not sure about Indian facilities, CAN, gas, and SIGI ones. I am not sure whether SCL has that capability. So if not, then there means, like that was pointed out, everyone. Okay, so Ashish is pointing out GAE Tech in Hyderabad has that capability. So yes, Ashish in that area here. Basically, this is, I think, if Ashish correct me if I'm wrong, but this is a government facility, right?
Yeah, gallium arsenide and gallium nitride both.
Yeah. So we have this for gas and GAN fabrication facility, government fabrication facility. And I don't think so. This is a funding question which I cannot answer. So plus, with respect to these GAN gas things, there are a lot of, since these are, especially GAN is used largely in defense applications, I do not know whether, means the information is not very easily available as well. Plus, even if there was information available, I mean, like Ashish cannot share that information with you. So. Okay, so things are running. It's 50% at my end. Yeah, so 66 will take time. The reason I am simulating at my end, so it will, I know it will finish at my end. It takes 10 minutes odd. So it will finish soon. And I wanted to show you the effect basically. So if it's not running at your end, let it finish at 9. In the meantime, we can take questions. No questions. Okay. So students really want the course to be over soon. Nice, but I really hope you made good use of the overall knowledge and the general breadth of the knowledge you wanted to cover with the respect to the 5G systems and millimeter wave systems, focusing on ASICs, and then a brief introduction of systems which we are giving today. And as we mentioned, this is all from open source tool perspective. So any researcher, any student, anyone who wants to get into this area can make use of this. And, it's good from the learning aspect. Okay. So this is just 30% left. I will let it finish in a couple of 2-3 more minutes. It should finish, and then we'll plot it. Then what is left next is this is the power spectrum density plot. We'll see the phase noise plot, and without the modulated signal, just the carrier phase noise plot. And then we'll try to see how we can change the noise characteristics or noise variance of different things. And then we'll try to see what is missing. Yes, Aditya, this is the transmitter signal plot. This is the transmitter signal plot with respect to the carrier. So the carrier has been taken out, so it is centered around 0. But yeah, we are saying if you see there's a frequency offset from carrier. So basically you are saying you're shifting it back to 0. Just because the way this function has been defined. You can go and read of so everything, how these functions are defined and everything. So everything is actually in your database. So your installation has everything. And you can modify them and you can create your own functions as well. That's why the tool is so powerful. You can write anything you want. So what about quiz 4 and quiz 5? What should we do about quiz 4 and quiz 5? Okay, so Rosanna is taking care of it. And this is, for sure, you can do entropy from this plot as well, means that's not defined here. So as I mentioned, the beauty of this tool is you can define any C++ function. You can take existing functions, you can define new functions. It's all editable from the back libraries. Means they're all there for you to play around with. Okay, last 10%, and then we'll look at a few other things. I really wanted to show you this effect. So this ran at my end. I don't know whether it ran at the other person's end, but I am going to plot this. And surprisingly, it is actually not giving any improvement, but it should. So let's see if my CPP sim resets again. So sometimes it does not load the new file. That would be really bad because we spent some time on this. So it is actually not loading the new file for some reason. So there is some issue. So we can look at this. The point which I was trying to make was if you increase the number of simulation points, then this plot should look really smaller. Sorry, smoother. So you get more points here. You have more data around your carrier. If you have more data around your carrier, this plot should have become lots smoother, basically. Okay, so you can actually see it from the other plot. So this is the test spectrum plot. And this plot is, yes, now it loads. So from the test spectrum, you can see that now this plot is a lot smoother and you get a lot of data. Basically from frequency offset from the carrier, you're seeing that most of the information is encoded within a 2 megahertz bandwidth, plus minus 2 megahertz bandwidth within from the carrier. That is your signal bandwidth, and almost all the information is encoded within that region. What we can do next is we can go back to our CPP sim and we change this. We changed it to say 20 and we close it. And what we can analyze is we can analyze just the without what is the effect without the actual encoding of the data. What will be the effect? We can analyze that by switching off the modulation. So the modulation gets switched off using this mod enable thing. And if we compile and run again, now my modulation has been switched off, okay? There is no modulation on my signal. So let me kill this. Let me plot, let this run quicker. And let's see, we'll save this and compile. So Kamra Bharat, anything fabricated in India, mainly in Hyderabad? Was that a question or a comment? I don't know. So what I've done now is I've switched off the modulation basically. And I'm running it with a smaller number of steps. What we'll do is we'll have to actually look at one last thing, which is the phase noise plot. So right now this is power spectrum plot. The last one is the phase noise plot. So phase noise for your carrier makes sense only if you do not have any modulator signal overlay on it. Otherwise, it doesn't make much sense. So this ran, and now we go back here, we close this. We do sync, and then we do a test. We leave this, we leave this, we leave this. What we have to go back and do is we need to change, where's that one? Not I signal. So this. So the high F and low F, let's make this 10 is 6 and 100 E3, and if we put that high F and low F limits, and then we take this thing, press on nodes, and plot this, we are able to get the phase noise plot. So yes, so this is our phase noise plot of just our transmit side VCO. Okay, and we can actually look at this. So that's the one, and okay, we have to look at the spectrum output here. So this one goes away, this one plotted here. Okay. So that was how you plot the phase noise. Now, the question comes, now we have learned all these analysis techniques. What all can we change from our system level side? So first of all, with the current setup, okay, what people have already modeled, given this small simulation setup you have, people here have, okay, so that, sorry, that went away. Let me close that. So to open that again. System. Okay, so what people have already modeled is, let me change that to 1, is if you go in here, and if you see each one of these blocks, right? So each one of these blocks have the characteristics associated with them. So your low pass filter, you can change the low pass filter gain. You can change its FP. You can change your VCO characteristics. You can actually change how your IQ signals are created, what Gaussian filters are used on top of it. What you can also do is you can go into the receiver, you can change your different filters over here. You can analyze this. What else can you do? What else can you do? Let me show you. You can also change your VCO characteristics of the receiver. You can change the channel. Now here we have modeled the channel just with the gain of 1/5. You can actually model this on a complex manner. You can write a complex channel over here. And especially with respect to the actual real world scenario, what you can do is you can actually pass noise into the system. So here, for example, your given VCO has certain offset noise characteristics associated with it. Had a noise at 20 megahertz offset of minus 165 dB. You can change its value and see what is the effect on your overall performance. Similarly, you can go into your receive side and you can add this noise over here. This noise var is actually controlled from the top as well by passing it as a variable, and you can add different values. You can add different strengths of noise and see what happens if your noise is good or bad. So how does this come into the overall picture? So in the overall picture, what you learned is different RF ASIC subcomponents, which were like power amplifiers, linear amplifiers, and all low noise amplifiers and all those things, right? Sorry, give me a moment. Okay, so with respect to the overall system, we had things like power amplifier, linear amplifiers, antennas, matching networks. So all of them at the end of the day have different characteristics, right? They have different characteristics like they have given gain, they have certain nonlinear coupling associated with them, they have noise associated with them. Multiple components may have noise associated with due to each other's presence. Your MIMO arrays, coupling might, everything can be modeled into a system level behavioral model, and you need to choose a correct level of abstraction, and this tool gives you a power to do that. So that is what our idea behind presenting this basic channel simulation and different aspects of it, that how you model different subcomponents and their nonlinearities and non-idealities was. Okay, so basically you can model all the effects. So your PA effects can be modeled, your LNA effects can be modeled, your transmission line effects can be modeled, your channels can be modeled, your filters matching how well everything connects, they can all be modeled behaviorally so that you are able to write a better system effectively. Now, I think people will again ask me, why can we not do it in MATLAB and ADSM and stuff like that? Basically, those are paid softwares. If as students you want to learn everything, all the concepts you think about, learn about in RF courses without the actual need to pay them. If you do an open source courses available like on NPTEL for free, and you actually want to design those things, learn those RF concepts, then that's when you use these tools like the Scikit RF tool, which Ashish taught you all the ASIC components. And now you take those ASIC components, you model their behavioral properties, and you put them into this tool. Gaurav, a PA model example, right now we have not put into this course because the PA model example becomes really complex. A very simple PA model is an amplifier. So what is an amplifier? You put a gain into your signal, right? That's your fundamental PA model. Now, because a PA is in a given has a bandwidth associated with it, so what you do is you'll now put a frequency dependent. You will put a frequency dependent amplification on it, and then because there are non-linearities associated with it, then you will add those non-linearities in terms of what is your gain if your if your signal strength is this, what is your gain if your signal strength is this? So you'll add those things on top of it. So you need to make those things. So the idea is from what we are trying to present is from overall system perspective and overall ASIC 5G domain perspective. If you have to do like study this area, what are the open source tools available to you? And that's the idea behind these sessions. So yeah, I think I covered most of the things I wanted to show from basic tool perspective. I wanted to leave some 15-20 minutes for Q&A, but it ended earlier than expected because I think most of the people were not actually running anything. So we can spend some 15-20 minutes if Ashish is here as well as me in terms of Q&A. And yeah, we can proceed that way. With respect to the general aspect of this course, how you can use this information, what other future possibilities are there, and all those things we can. So the C++ code is inside your install directory, Aditya. You can go and open that. That's I don't want to explore my directory right now, but it's all in your install directory. And the CPPSIM website actually gives you all the information as to how you can add to the model. Since this is an open source tool, you can actually tinker with the tool. This is based off of MIT, and if you tinker with the tool and if you send it to them, they actually will take into account and add it into their tool as well. That's how this tool has been made. Basically, students have made this tool. And this Professor Perro, who is the lead for this, he is a legendary person basically in this area. Anything else you want to add, Ashish? No? Okay. Yes, means I'm open to questions. I'll wait for another 5-10 minutes. Okay, so basically the installation might not have had that. Some version might have been different. What we can do is we can paste these files these are present. So I can put these files in a drive and give them to you. So in the drive which you have, I can send these files around. Because these are open source files, I'm allowed to do it. So I'll just send those files to everyone. Does that answer your question, Vaishnavi? Which error are you getting? Oh, okay. So I think it's some installation error. So how many do you have a 32-bit Windows or 64? So that should not be an issue. Just redo the whole installation procedure. Make sure you install those DLL packages which we talk about in the installation file. Usually we have run like a huge course with this thing as well. We have not. We have seen that sometimes there are installation issues, and eventually everyone, if a nice clean installation, is able to run this. We have not had issues. This is quite stable tool if run in the correct version. Okay. Firoza ma'am, I think we are half an hour early, but I thought we will have more questions with respect to how the tool runs. Since people on the 10th day do not have the energy to ask questions, I think we ended up half an hour early. So what should we do? I don't see any more questions.
Hello. Yeah. Thank you, Aditya sir.
Yeah. Basically,
Yeah.
there are no more questions. I wanted since I think in the 10th day, everyone's tired and don't want to ask questions. So it ended quicker than I expected.
Okay, sir. So if the participants are not having any more queries, so we can end the session for now.
Yeah.
So we'd like to thank Ashish sir, Aditya sir, for your continuous sessions. And the announcement to participants is that the feedback link is in the drive. So we request you all to please give your genuine feedback that could help us to improve in our future FDPs. And please join by 3 p.m. for the valedictory session. So we'd also request Ashish sir and Aditya sir also to please join us for the valedictory session at 3 p.m.
Yes, ma'am. Sure. Thank you.
Thank you, sir.
Vijaya, your question, you can make a tool for EVM basically. Yes, ma'am. Basically, I was saying you can add it on the tool. So that's we can write a C++ code on top of it. I think that's all. So I think that's all that. But you need to write a C++ code basically. Okay. Yes, ma'am. That's all.
Thank you, sir. So any more queries for like from any participants? Or else we'll end this event now. We'll not end the link. It will be active. So we'll request you to please get connected again by 3 p.m. And Kavita ma'am, the
Perfect.
feedback link is in the drive. So you may please find over there.
Perfect. Thank you. Thank you for coordinating everything.
Thank you, sir.
Yeah. Bye.
Bye.